The morning of August 28, 1944. Dover, England. A Royal Artillery gunner pressed his eye against the rubber cup of a predictor sight, tracking a small cruciform shape racing across the summer sky at 350 miles per hour. The droning pulse of its engine, a sound Londoners had learned to dread, cut through the coastal air. But this morning, something was different. The shells leaving the 3.7-inch anti-aircraft guns weren't bursting where the predictor calculated the target would be in 8 seconds. They were detonating the instant they passed within 70 feet of the flying bomb itself, without any apparent contact. The gunner watched in fascination as the 5th V-1 of the morning disintegrated in mid-air, its warhead tumbling uselessly into the channel. By sunset, his battery would help destroy 82% of every flying bomb that crossed the English coast that day. The Germans, watching their revolutionary terror weapon rendered nearly obsolete in a single 24-hour period, would have no explanation for what had just happened. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This wasn't supposed to be possible. The Vergeltungswaffe, one vengeance weapon. One represented the cutting edge of German engineering, a pilotless aircraft that flew too fast and too low for conventional interception. Since the first V-1 had crossed the Channel on June 13, 1944, exactly 1 week after D-Day, these flying bombs had terrorized southern England with a form of warfare the world had never seen. They were meant to be unstoppable. Yet on that late August morning, the entire calculus of the V-1 campaign shifted because of a device so secret that the British gunners using it had no idea what made their shells so suddenly, devastatingly effective. Inside each artillery round sat a technological breakthrough that would change not just this battle, but the entire future of aerial warfare. The variable time fuse, known in classified documents simply as VT. The story of how American scientists turned the V-1 from an unstoppable terror weapon into target practice in less than 3 months is not just a tale of technological triumph. It's a narrative about the collision between two fundamentally different approaches to warfare: German engineering confidence in mechanical precision versus American faith in electronic innovation. More profoundly, it reveals how a single technological advantage, properly deployed, could render months of enemy engineering effort nearly worthless in a matter of hours. The VT fuse didn't just shoot down flying bombs. It shattered the psychological warfare campaign the V-2 represented, and it did so with a device small enough to fit inside an artillery shell, yet sophisticated enough that its operating principles would have seemed like science fiction to most military planners just 5 years earlier. To understand the magnitude of what happened on August 28th, you need to understand what the V-1 was, what it represented to both the Germans and the Allies, and why every conventional defensive measure had proven inadequate against it. The V-1 was not a missile. In the modern sense, it had no guidance system, no ability to change course or seek targets. It was essentially a flying bomb, a pilotless aircraft packed with 1,850 pounds of amatol explosive, launched from a ramp by a steam catapult and guided only by a simple gyroscopic autopilot and a mechanical odometer that counted down the distance to target. When the odometer reached 0, the fuel supply cut off, the engine stopped, and gravity did the rest. But this simplicity was the V-1's strength, not its weakness. German engineers at the Fieseler works had created a weapon that could be mass-produced cheaply and quickly. Unlike a bomber, it required no crew, no years of pilot training, no recovery operations if it failed to return. Unlike a rocket like the V-2 that would follow it, used a pulse jet engine that ran on low-grade fuel rather than exotic liquid propellants. Each V-1 cost approximately 5,000 Reichsmarks to produce, roughly the equivalent of $5,500 in 1944 American currency. A single Lancaster bomber cost 60 times that amount. The calculus was brutally simple. Germany could produce V-2 faster than Britain could replace the housing they destroyed, and do so without risking a single trained airman. The weapon's designation told you everything about its intended purpose: Vergeltungswaffe vengeance weapon. This wasn't a military device designed to destroy military targets. It was explicitly conceived as a terror weapon, retaliation for the Allied bombing campaign against German cities. Hitler himself had demanded weapons that would strike fear into British civilians, that would make them pressure their government to seek peace terms. The V-1 achieved this psychological impact not despite its mechanical simplicity, but because of it. The characteristic sound of its pulse jet engine, a harsh, droning buzz that gave the weapon its British nickname, the buzz bomb or doodlebug, announced its approach with terrifying clarity. Londoners learned to listen for the moment when that sound stopped, because silence meant the bomb was falling toward them. You heard it coming, you heard it cut out. Then you had perhaps 15 seconds before impact and detonation. By late June of 1944, just 2 weeks after the first V-1 attack, more than 2,000 flying bombs had been launched at London and southern England. The British government, which had successfully hidden the extent of German conventional bombing casualties earlier in the war, found itself unable to conceal the V-1 threat. The weapons struck at all hours, without warning beyond that terrible droning approach, and they hit civilian areas with no discrimination whatsoever. A single V-1 that struck the Guards' Chapel at Wellington Barracks during Sunday service on June 18th killed 119 people and wounded another 121. The psychological impact rippled through London. These were not bombs dropped by aircraft that could be shot down or deterred. These were machines, tireless and inhuman, that came day and night regardless of weather, regardless of fighter opposition, regardless of anything the defences could throw at them. The British defence establishment threw everything they had at the V-1 problem. Fighter Command assigned the fastest aircraft in the RAF inventory to anti-doodlebug patrols, Hawker Tempests, Gloucester Meteors, even specially lightened Spitfire Mark XIVs with their engines modified to squeeze out every possible knot of speed. The tactics were desperate and dangerous. A V-1 flew at 350 miles per hour at altitudes between 2,000 and 3,000 feet, fast enough that only the newest fighters could catch it, and low enough that shooting it down risked the explosion, destroying the pursuing aircraft. Some pilots resorted to flying alongside the V-1 and using their wingtip to flip the flying bomb's wing, tumbling it out of control. This worked, but required nerves of steel and perfect judgment of distance and airspeed. Anti-aircraft guns formed a second defensive belt. The British reorganised their entire southern defence network, creating a gun belt along the coast and another ring around London itself. 8 heavy anti-aircraft regiments deployed along the Channel coast with 3.7-inch guns, supplemented by lighter automatic weapons. The mathematics of hitting a V-1 with conventional anti-aircraft fire were brutally unfavourable. The shell had to be fused to detonate at precisely the altitude the V-1 would occupy, and it had to arrive at the exact 3-dimensional point in space within the second and a half. The flying bomb took to traverse the kill radius of the explosion. Against a manoeuvring aircraft, this required prediction, but prediction based on a pilot's likely evasive actions. Against a V-1 flying straight and level, it should have been simpler. In practice, it wasn't. The problem was the fuse. Every anti-aircraft shell fired in 1944 used time fuses, mechanical clockwork devices, set before firing to detonate the shell at a calculated moment after leaving the gun. These fuses were precision instruments, manufactured to tolerances measured in thousandths of a second, but they were still mechanical clocks subjected to the enormous acceleration of firing 15,000 times the force of gravity in the instant the shell left the barrel. Minor variations in the powder charge, microscopic differences in air density and temperature, even the rotation of the Earth all affected where the shell would be when the fuse triggered detonation. A gunner could calculate everything perfectly. The predictor could solve the ballistic equations flawlessly, and the shell might still detonate 50 feet away from the target, close enough to see, far enough to be worthless. The statistics told the story. Through June and July of 1944, anti-aircraft guns along the British coast fired thousands of rounds at hundreds of V-1s second. Their kill rate hovered around 4%. 4 shells out of every 100 fired actually destroyed their targets. This wasn't a failure of courage or effort. The gun crews worked themselves to exhaustion, firing drill after drill, calibrating and recalibrating their predictors. It was a failure of the fundamental technology. Mechanical time fuses simply weren't accurate enough to reliably hit a small, fast-moving target. The only reason the defences destroyed any V-1s second at all was the sheer volume of fire they threw into the sky. Barrage balloons formed the third line of defence. Hundreds of balloons tethered along likely approach routes at altitudes between 5,000 and 7,000 feet. Their steel cables designed to slice through the wings of any aircraft foolish enough to fly into them. The V-1s second flew lower than the balloon barrage, rendering them nearly useless. Some V-1s second struck cables by accident, but the percentage was negligible. The balloons served mostly to make Londoners feel that something was being done, that the government had a plan. The reality was grimmer. Britain's layered air defence network, the most sophisticated in the world, refined through 4 years of war against the Luftwaffe, was proving nearly impotent against an unsophisticated flying bomb. By early August, the situation had become critical. The Germans were launching an average of 100 V-1s second per day. British fighters shot down about 25% of the flying bombs that reached the coast, but only if weather permitted visual interception. Anti-aircraft guns destroyed another 4 to 5%. The rest, roughly 70 V-1s second every day, penetrated to London and the surrounding areas. The casualty rate climbed steadily. By the end of August, the V-1 campaign would kill more than 6,000 people and seriously injure nearly 18,000 more. Hundreds of thousands of Londoners had evacuated the city. Industrial production was disrupted, and morale, the explicit target of Hitler's vengeance weapon, was cracking. Churchill's government faced a terrible calculus. The Normandy invasion was succeeding, but slowly. Allied forces had broken out of the beachhead only in early August, and the launch sites in the Pas de Calais, the region of France closest to England, remained beyond reach. Intelligence estimates suggested the Germans had prepared dozens of launch sites and had stockpiled thousands of V-1s second. If the current rate continued, tens of thousands more casualties were inevitable. And worse was coming. Intelligence reports spoke of a second vengeance weapon, the V-2 rocket, against which there would be no defence at all. It travelled too high and too fast for any interception. The V-1 campaign had to be broken, and it had to be broken quickly, before German vengeance weapons shattered British civilian morale and potentially forced a negotiated end to the war in the West. What neither the British public nor the German military planners knew was that American scientists had been working for 3 years on a device that would solve the fundamental problem of anti-aircraft fire. They'd been working on it in secret facilities, under security so tight that even most military planners didn't know the project existed. They'd been working on it not specifically to counter the V-1, the weapon hadn't been deployed yet when the proximity fuse project began, but to solve the general problem of shooting down aircraft reliably. The fact that their invention would prove devastatingly effective against Germany's most advanced terror weapon was almost coincidental. The story of the VT fuse begins not in 1944, but in 1940, in the laboratories of American universities and defense contractors. British scientists had recognized the proximity fuse problem during the First World War, a shell that could detect its own nearness to a target and detonate automatically would revolutionize anti-aircraft warfare. But the engineering challenges seemed insurmountable. You needed a radio transmitter and receiver small enough to fit inside an artillery shell. It needed to survive the acceleration of firing forces that shattered conventional vacuum tubes instantly. It needed to generate and detect radio waves, process the reflected signal, and trigger a detonator, all while spinning at hundreds of revolutions per second as it flew through the air. And it needed to do all this reliably, cheaply enough for mass production, and simply enough that ordinary gunners could use it without specialized training. The British had experimented with photoelectric fuses, devices that would detonate when a shadow passed over a light sensor. These worked in laboratory conditions but proved useless in combat, where smoke, clouds, and the flash of other exploding shells triggered false detonations constantly. They'd experimented with acoustic fuses that listened for aircraft engines, but these couldn't distinguish between friendly and enemy aircraft, and the noise of battle overwhelmed their sensors. By 1940, British researchers had concluded that a practical proximity fuse was probably impossible with current technology. They were wrong, but their pessimism was understandable. The physics were straightforward. The engineering was extraordinarily difficult. American researchers approached the problem from a different angle. In the summer of 1940, with Britain under sustained German air attack and war increasingly likely for the United States, the National Defense Research Committee established Section T. The T stood for Fuse, to investigate proximity fuse development. The section's director, Merle Tuve, was a physicist at the Carnegie Institution who'd done pioneering work in radar before the war. Tuve understood radio wave propagation, and he understood that the basic principle of radar: transmit a signal, measure its reflection, could theoretically be miniaturized into an artillery fuse. Theoretically. The practical challenges were immense. A conventional anti-aircraft shell measured about 4 inches in diameter and 14 inches long. Inside that space, you needed to pack a radio transmitter operating at frequencies high enough to detect aircraft at useful ranges, a receiver sensitive enough to pick up reflected signals from hundreds of feet away, amplification circuitry to process those signals, a discriminator circuit to distinguish reflected signals from background noise, a firing circuit to trigger the detonator, and batteries to power everything, all while leaving room for the explosive charge the shell was meant to deliver. Every component had to survive 15,000 times. The force of gravity during firing had to function in temperatures ranging from -40 to +120 degrees Fahrenheit, had to work while spinning at hundreds of rotations per second, and had to be manufacturable by the thousands. The vacuum tube problem nearly killed the project before it began. Every electronic component in 1940 depended on vacuum tubes, glass bulbs containing heated filaments and metal plates, evacuated of air to allow electrons to flow in controlled ways. Vacuum tubes were fragile. Drop a radio, and you'd likely shatter one of its tubes. Subject a tube to 15,000 times the force of gravity, and it would simply explode into fragments. Section T needed tubes that could survive forces no vacuum tube had ever encountered, and they needed them to be small enough, cheap enough, and reliable enough for mass production. The breakthrough came from an unexpected source: the Raytheon Company, a Massachusetts manufacturer that had been producing vacuum tubes for home radios. Raytheon's engineers developed a tube so radical it seemed impossible, a tube with no conventional base, with the filament and plates suspended by wire supports instead of mounted on a rigid socket, with every internal component designed to flex and absorb shock rather than resist it. They made the tubes smaller, about the size of a man's thumb. They made them rugged, able to withstand not just the shock of firing but the constant vibration and spinning of flight. Most remarkably, they made them work reliably. By late 1941, Raytheon was producing proximity fuse tubes that could survive 15,000 times the force of gravity and still function perfectly. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. With the tube problem solved, Section T faced the next challenge: getting the fuse to distinguish between the rapid increase in reflected signal that meant a target was near versus the gradual changes in signal caused by approaching the ground or passing near structures. The mathematics were complex. As the shell approached a target aircraft, the strength of the reflected radio signal increased according to the inverse fourth power of the distance, double the distance, and the signal strength decreased by a factor of 16. This rapid change in signal strength was the signature of a nearby target. But the shell was also approaching the ground constantly, and ground reflections would eventually trigger the fuse if it wasn't discriminating enough. The solution involved careful selection of the radio frequency and the sensitivity of the receiver. The fuse transmitted at around 200 MHz, a frequency that provided good reflection from aircraft but was partially absorbed by ground vegetation and structures. The receiver was designed to trigger only when the reflected signal increased at a rate consistent with approaching a solid target at speeds typical of aircraft or V-1 flying bombs. In practical terms, this meant the fuse would detonate when the shell passed within about 70 feet of a target, close enough that the shell's fragmentation pattern would be lethal to an aircraft, but far enough that minor variations in trajectory didn't matter. By late 1942, Section T had produced working prototypes. The fuses worked. They survived firing. They reliably detonated near test targets. The security implications were immediately obvious. If a VT-fused shell failed to detonate and fell into enemy hands intact, German or Japanese engineers could reverse engineer the technology and potentially deploy it against Allied aircraft. The decision was made to restrict VT fuse use to situations where the risk of capture was minimized. Initially, this meant naval use only, where shells that missed would fall into the ocean. The fuse's first combat deployment came in January of 1943, when the cruiser USS Helena used VT-fused 5-inch shells to destroy a Japanese aircraft attacking in the Solomon Islands. The results were dramatic. The Helena's gunners shot down the aircraft with just 6 shells, a success rate unimaginable with conventional time fuses. Through 1943 and into 1944, VT fuse production ramped up. The manufacturing challenges were nearly as daunting as the engineering challenges. Each fuse contained 4 vacuum tubes, multiple capacitors and resistors, batteries, a small transmitting antenna, and the firing circuit, 25 components total, all assembled by hand, all tested for functionality and shock resistance. The specifications were rigid. Every fuse had to function after being subjected to 20,000 times the Chaffel force of gravity, had to transmit at the correct frequency within narrow tolerances, had to maintain battery charge for months of storage. Defect rates in early production ran above 30%. By mid-1944, with multiple manufacturers producing fuses around the clock, defect rates had dropped below 5%, and production had reached several 100,000 fuses per month. The U.S. Navy used VT fuses extensively in the Pacific, where their effectiveness against Japanese kamikaze attacks proved devastating. Japanese pilots discovered that aircraft diving toward American ships began exploding in mid-air well before they reached their targets. The psychological impact on Japanese aircrews was significant, but the strategic impact was more important. VT-fused anti-aircraft fire was roughly 5 times more effective than conventional fire. Shells that once required 50 or 60 rounds to down an aircraft now needed 10 or 12. The difference wasn't just efficiency, it was survival. Ships that might have been overwhelmed by massed kamikaze attacks instead survived because their defensive fire became lethal at much greater ranges. But the European theatre remained off-limits for VT fuse deployment. The risk of ground forces capturing intact fuses was too high, and the Allied air forces had achieved such dominance over German airspace by 1944 that VT fuses seemed unnecessary. German air raids against Britain had dwindled to nuisance level. The Luftwaffe was conserving its strength, reeling from cumulative losses. The air war appeared won without needing to reveal America's secret weapon. Then, on the morning of June 13, 1944, exactly 1 week after D-Day, the first V-1 flying bomb crossed the English Channel and impacted in London. Within hours, British intelligence had assessed the threat. Germany had deployed a weapon against which conventional defences were proving inadequate. Within days, requests reached American military planners. Could the VT fuse be deployed against the V-1 threat? The answer involved complex calculations of risk versus benefit. If VT-fused shells were used on land, some percentage would fail to detonate and could be recovered by German forces. But if the V-1 campaign continued unchecked, the strategic and psychological consequences could be catastrophic. By late July, the decision was made. VT fuses would be deployed to British anti-aircraft batteries defending against the V-1 threat. The security restrictions were extraordinary. British gun crews were told only that they were receiving a new type of ammunition that would significantly improve their accuracy. They were forbidden from approaching any dud shells, which were to be immediately reported and recovered by specialized teams. The fuses themselves bore no external markings that would reveal their function. To anyone examining an unfired round, they would appear to be conventional mechanical time fuses. Only in the moment of firing, when the setback force of acceleration activated the batteries and initiated the radio transmission, would the fuse reveal its true nature. The first VT-fused rounds were issued to British anti-aircraft batteries along the Channel coast in early August of 1944. The gun crews loaded them, aimed at incoming V-2 using their conventional predictors, and fired. What happened next seemed like magic. The shells detonated in proximity to the V-2 without any visible contact. Gun crews watched through binoculars as their rounds exploded precisely when they passed near the flying bombs, sending shrapnel through the pulse jet engines and wing structures. V-2, that had seemed untouchable days before, now tumbled from the sky with startling regularity. The gunners didn't understand how their shells knew when to detonate. They only knew that suddenly, impossibly, they were hitting targets they'd been missing for weeks. The effectiveness increased as crews gained experience with the new ammunition. Unlike mechanical time fuses, which required precise calculation of the target's future position and the exact time of flight, VT fuses were far more forgiving. A gunner could aim at where the V-1 appeared to be heading, fire, and trust that if the shell passed anywhere within 70 feet of the target, the fuse would trigger detonation automatically. This transformed anti-aircraft gunnery from a precise mathematical exercise into something closer to area saturation. Instead of trying to place a single shell in a specific cubic volume of sky at a specific instant, gunners could fill a general area with shells, knowing that any shell passing near the target would automatically detonate. The tactical implications became clear within days. Anti-aircraft batteries that had been destroying 4% of incoming V-2 in July were destroying 20, then 30, then 40% by mid-August. Fighter Command noticed the change immediately. Fewer V-2 were penetrating the coastal gun belt, which meant fewer targets for the Tempests and Spitfires patrolling inland. The barrage balloon operators noticed it too. Fewer flying bombs were making it far enough inland to threaten the balloon defences. Most importantly, Londoners noticed. The number of V-1 impacts in the city dropped dramatically. The constant wail of air raid sirens that had characterized July and early August began to diminish. German intelligence officers, monitoring the defensive effectiveness from across the Channel, noticed the change as well, but they couldn't explain it. The number of V-2 being launched hadn't decreased. If anything, the launch crews were becoming more efficient, maintaining steady firing rates despite Allied air attacks on the launch sites. Yet, the percentage of V-2 reaching their targets was dropping precipitously. Some German analysts suggested that British fighter tactics had improved, that the RAF had deployed faster aircraft, developed better interception procedures. Others suggested that the flying bombs themselves were suffering from quality control problems, that rushed production was resulting in unreliable engines or guidance systems. No one suggested the truth that American scientists had solved a fundamental problem of physics and engineering, and that British anti-aircraft shells were now detonating by radio proximity rather than mechanical timing. The morning of August 28, 1944, represented the culmination of the VT fuse deployment. By this date, Virtually all anti-aircraft batteries defending the Channel coast had been supplied with VT-fused ammunition. The gun crews had weeks of experience with the new rounds. The predictor operators had refined their techniques, understanding that they no longer needed to calculate exact detonation points. They needed only to place shells in the general vicinity of the target's flight path. The weather that morning was clear, visibility excellent, conditions that favoured both the German launch crews and the British gunners. The Germans launched 97 V-1 flying bombs at England on August 28th. This was typical for late August. The launch rate had been steady since early summer, with the Germans maintaining pressure on British civilian morale, while Allied ground forces slowly advanced through France toward the launch sites. What wasn't typical was what happened to those 97 flying bombs. Of the 97 V-1s second launched, 91 crossed the English coast and entered the defensive zone where anti-aircraft batteries were deployed. The remaining 6 either failed shortly after launch or were destroyed by Allied fighters over the Channel before reaching the coast. Once the 91 V-1s second entered the gun belt, the statistics became remarkable. Anti-aircraft batteries using VT-fused ammunition destroyed 75 of them. 75 out of 91, an 82% kill rate. To understand how extraordinary this was, consider that just 2 months earlier, in late June, anti-aircraft guns were destroying 4% of incoming V-1s second. On August 28th, using the same guns, manned by the same crews, firing at the same targets following the same flight profiles, the kill rate was 82%. The only variable that had changed was the fuse. Every other factor, gun types, crew training, predictor equipment, target characteristics, remained constant. The VT fuse alone had increased defensive effectiveness by a factor of 20. The day's engagement demonstrated several key advantages of proximity fusing. First, the sheer increase in hit probability meant that fewer shells were required per kill. Where a mechanical time-fused engagement might require 50 or 60 shells to down a V-1, a VT-fused engagement typically required 10 to 15 shells. This wasn't just a matter of ammunition conservation, it meant that gun batteries could engage multiple targets in rapid succession without exhausting their ammunition supplies. A battery that previously might engage 2 or 3 V-1s second before needing to resupply could now engage 8 or 10. Second, the VT fuse reduced the skill threshold required for effective gunnery. Calculating precise time fuses required experienced predictor operators who could account for wind, air density, shell ballistics, and target trajectory simultaneously. Small errors in any of these calculations resulted in misses. VT fuses were far more forgiving. As long as the shell passed reasonably close to the target, the fuse would trigger. This meant that even relatively inexperienced gun crews could achieve high kill rates. In a military context where experienced personnel were increasingly scarce and training time was limited, this was a significant operational advantage. Third, and perhaps most important from a tactical standpoint, VT fuses were effective against targets at varying altitudes without requiring fuse resetting. Mechanical time fuses had to be set based on the predicted altitude of the target at the moment of interception. If the target changed altitude, or if the initial altitude estimate was wrong, the shell would detonate above or below the target. V-1s second typically flew at altitudes between 2,000 and 3,000 feet, but individual flying bombs varied by several hundred feet depending on fuel load, launch conditions, and guidance system peculiarities. VT fuses eliminated this source of error entirely. The fuse didn't care what altitude the target was at, it cared only about proximity. The technical details of how the VT fuse functioned in combat reveal the elegance of its design. As the shell left the gun barrel, the enormous acceleration, 15,000 times the force of gravity sustained for approximately 15 thousandths of a second, activated the fuse. A setback switch closed, completing the electrical circuit and connecting the batteries to the transmitter and receiver circuits. The acceleration also served as a safety mechanism. The fuse couldn't possibly activate accidentally during handling or storage because only the force of firing could close the setback switch. Once activated, the transmitter began broadcasting a continuous wave radio signal at approximately 200 MHz. This frequency was chosen carefully. Lower frequencies would have required larger antennas that couldn't fit in the fuse package. Higher frequencies would have been absorbed by atmospheric moisture and been less reliable in poor weather. 200 MHz provided good range. The fuse could detect aircraft at distances up to 200 feet while still allowing for compact antenna design. The radio wave propagated outward in all directions from the spinning shell. As the shell approached a target, a V-1 flying bomb, in this case the radio waves struck the metal structure of the flying bomb and reflected back toward the shell. The reflected waves were detected by the fuse's receiver, amplified by the vacuum tube circuits, and compared to the transmitted signal. This comparison revealed something crucial. The frequency of the reflected signal was slightly different from the transmitted signal due to the Doppler effect. As the shell approached the V-1, the reflected radio waves were compressed, their frequency increasing. The rate of frequency change was proportional to the rate at which the distance between shell and target was decreasing. The discriminator circuit in the fuse measured this Doppler shift. When the rate of frequency change exceeded a predetermined threshold, indicating that the shell was passing within approximately 70 feet of a solid target, the discriminator triggered the firing circuit. The firing circuit sent a current through a small electrical detonator, which initiated the shell's main explosive charge. From the moment the reflected signal crossed the threshold to the moment of detonation, less than 1/1000th of a second elapsed. The shell exploded, sending fragments in all directions. If the fuse had functioned correctly, if the 70-foot proximity was accurate, those fragments would shred the thin aluminum skin of the V-1's fuselage, sever control wires, puncture fuel lines, or damage the pulse jet engine. Any of these outcomes would cause the flying bomb to crash. The effectiveness of the VT fuse against V-2 was particularly high because the V-1 was, in many ways, an ideal target for proximity-fused ammunition. It flew straight and level, maintaining constant altitude and heading. It presented a relatively large radar cross-section. The metal fuselage and wings reflected radio waves efficiently. It had no armor and no redundant systems. Any significant damage would cause a crash. And perhaps most importantly, it couldn't take evasive action. A human pilot, seeing shells bursting nearby, would maneuver violently, making the gunner's job harder. The V-1 simply flew onward into the exploding shells, its simple mechanical autopilot incapable of recognizing danger or responding to it. The psychological impact of August 28th's success rippled through both Allied and German command structures. For the British, the day represented vindication of the decision to deploy VT fuses, despite the security risks. The technology worked precisely as American scientists had promised, and it worked at a scale that exceeded even optimistic predictions. An 82% kill rate meant that the V-1 threat, while not eliminated, had been reduced to nuisance level. Flying bombs that penetrated the coastal gun belt were then engaged by fighters and by the gun belt surrounding London itself, also equipped with VT-fused ammunition. The layered defence, which had been porous in June and July, had become nearly impenetrable by late August. For German planners, August 28th marked a turning point they didn't fully understand but couldn't ignore. The V-1 campaign, which had begun with such promise in mid-June, was failing. Thousands of flying bombs had been produced, dozens of launch sites prepared, and enormous resources devoted to the Vengeance weapon program. Yet by late August, fewer than 20% of launched V-2 were reaching their intended targets. The Germans had no explanation that accounted for the sudden increase in defensive effectiveness. Some intelligence officers suspected a new type of ammunition, but the security surrounding VT fuses was so tight that no intact examples had been recovered. German engineers, without access to the actual technology, couldn't deduce its operating principles from observation alone. The strategic implications extended beyond the V-1 campaign. The VT fuse represented a category of weapon that military theorists had discussed but never successfully deployed, a truly intelligent munition that could make autonomous decisions about when to detonate. Previous attempts at smart weapons, acoustic torpedoes, photoelectric bombs, had proven unreliable in combat conditions. The VT fuse demonstrated that electronic sensing and decision-making could function in the most demanding environment imaginable. Inside an artillery shell subjected to enormous acceleration, spinning at hundreds of rotations per second, traveling at supersonic speeds through varying atmospheric conditions. The success against V-2 validated the massive investment in VT fuse development. By August of 1944, American industry was producing more than 1 million proximity fuses per month. Production facilities at Eastman Kodak, Sylvania, and dozens of other contractors operated around the clock, assembling the delicate components by hand, testing each fuse multiple times, packing them for shipment to combat theaters around the world. The unit cost had dropped from over $30 per fuse in early production to under $20 by mid-1944, still expensive compared to a mechanical time fuse that cost about $2. But the tenfold increase in effectiveness more than justified the additional expense. The technology's potential applications extended far beyond anti-aircraft use. The U.S. Army had begun experimenting with VT fuses in artillery shells used for ground bombardment. A shell that detonated 20 or 30 feet above the ground, rather than on impact, would be devastating against troops in the open. The fragmentation pattern from an air burst covered a much larger area than a ground burst, and there was no ground absorption of the blast to reduce effectiveness. Early tests suggested that VT-fused artillery rounds were roughly 3 times more effective against infantry than impact-fused rounds. This had profound implications for artillery doctrine. The traditional mathematics of fire missions, based on impact bursts, would need to be completely revised. Naval applications proliferated. Beyond anti-aircraft, to use, VT fuses proved effective in shore bombardment roles. A shell fused to detonate at a specific altitude above ground could strike the upper floors of buildings or detonate above fortifications where troops had taken cover. The U-10. Navy began developing specialized shore bombardment ammunition using VT fuses, designed to trigger at altitudes as low as 10 feet, creating devastating fragmentation patterns against coastal defenses. The Japanese defenders at Iwo Jima and Okinawa would experience the full effect of VT-fused shore bombardment, with pre-invasion bombardments achieving casualties rates significantly higher than those achieved with conventional ammunition. But in August of 1944, these future applications remained classified and largely theoretical. The immediate, visible success was the near neutralization of the V-1 threat. Between August 20th and September, first a 12-day period during which VT fuse deployment reached its maximum extent, British anti-aircraft defences destroyed more than 70% of all V-1s, second that crossed the coast. Combined with fighter interceptions and the small percentage of V-2 that failed due to mechanical problems, fewer than 15% of launched flying bombs reached London during this period. The human cost of the V-1 campaign, while still significant, was far lower than it would have been without VT fuses. From June 13th to September 1st, the peak period of V-1 attacks, approximately 6,000 people were killed by flying bombs in London and southern England, with another 18,000 seriously wounded. These casualty figures, while tragic, represented a small fraction of what German planners had hoped to achieve. Intelligence estimates suggested that if the V-1 campaign had continued at its early effectiveness rate, with 70% of launched bombs reaching their targets, casualties by September could have exceeded 20,000 dead and 60,000 wounded. The VT fuse, by increasing defensive effectiveness by a factor of 20, saved tens of thousands of lives during the late summer of 1944. The V-1 campaign effectively ended in early September as Allied ground forces overran the launch sites in the Pas-de-Calais region. The last major V-1 attack on London occurred on September 1, 1944. Some launches continued from modified aircraft and from sites in the Netherlands through March of 1945, but the scale was greatly reduced, and defensive measures dominated by VT-fused anti-aircraft fire destroyed the vast majority of these late-war flying bombs before they reached their targets. The German response to the failure of the V-1 campaign was to accelerate deployment of the V-2 rocket, a weapon against which no defense existed. The V-2 traveled too fast and too high for interception. It reached altitudes above 50 miles and impacted at speeds exceeding 3 times the speed of sound. No fighter could catch it, no anti-aircraft gun could engage it, and no proximity fuse could help against a target that arrived without warning and impacted before the sound of its passage reached the ground. But the V-2 was enormously expensive. Each rocket cost approximately 100,000 Reichsmarks, 20 times the cost of a V-1, and Germany's industrial capacity was collapsing under Allied bombing. Fewer than 3,000 V-2 seconds were launched during the entire war, compared to more than 10,000 V-1 second. The Vengeance weapon campaign, which had begun with hopes of breaking British morale and forcing peace negotiations, ended with Germany expending enormous resources to achieve minimal strategic effect. The broader legacy of the VT fuse extended far beyond the Second World War. The basic principles developed in the early 1940s miniaturized radio transmission and reception, Doppler discrimination, shock-resistant electronics became foundational technologies for post-war weapons development. Every modern missile, every smart bomb, every precision-guided munition traces its lineage back to the proximity fuse. The idea that a weapon could sense its environment and make autonomous decisions about when to detonate became standard rather than revolutionary. The Cold War arms race saw proximity fusing technology evolve in multiple directions. Air-to-air missiles used increasingly sophisticated radio and infrared proximity fuses to detonate near enemy aircraft. Surface-to-air missiles incorporated proximity fuses that could discriminate between aircraft and decoys. Artillery shells gained the ability to count targets beneath them and detonate over concentrations of vehicles or troops. Anti-tank weapons used downward-looking proximity sensors to detonate above armored vehicles, where armor was thinnest. In every case, the fundamental principle remained the same: sense the target, measure proximity, detonate when optimal effect can be achieved. The VT fuse also influenced post-war electronics development in unexpected ways. The miniaturization techniques developed to fit radio circuits into artillery shells contributed to the broader trend towards smaller, more reliable electronic devices. The shock-resistant vacuum tubes developed by Raytheon influenced designs for tubes used in harsh environments, military radios, aircraft, electronics, even early computers. The transition from vacuum tubes to transistors in the 1950s was accelerated by engineers who'd learned, working on proximity fuses, that electronic components could be made far smaller and more reliable than pre-war practice had suggested. From a historical perspective, the VT fuse represents a particular type of technological warfare, the kind where a single innovation, properly applied, can render an opponent's costly investment nearly worthless. Germany had devoted enormous resources to the V-1 program: research and development, production facilities, launch infrastructure, thousands of tons of raw materials. The program was meant to terrorize Britain into seeking peace terms, or at minimum to divert Allied resources away from the invasion front. Instead, an American device, no larger than a coffee cup, produced for $20 apiece, destroyed the program's effectiveness in a matter of weeks. This pattern, technological counter to technological threat, would repeat throughout the Cold War and into the modern era. Every advance in offensive capability would be met, eventually, by defensive innovation. Every unstoppable weapon system would prove vulnerable to some clever application of physics or engineering. The V-1 and the V-2 fuse were early examples of this dynamic, but they established a template that military planners would follow for decades. Identify the vulnerability in the enemy's system, develop a specific counter, deploy it before the enemy can adapt. The security classification of the V-2 fuse was finally lifted in 1945, after the war in Europe ended and the risk of German reverse engineering disappeared. American and British scientific journals published detailed accounts of the fuse's development, praising it as one of the war's most significant technical achievements. The scientists involved Merle Tuve and his team at Section T, the engineers at Raytheon, the hundreds of physicists and technicians at universities and contractors across America received recognition for their work. Popular accounts appeared in newspapers and magazines, explaining in simplified terms how American ingenuity had defeated Germany's vengeance weapons. But perhaps the most significant recognition came from those who'd witnessed the technology in action. British anti-aircraft crews, who'd spent weeks firing thousands of rounds for negligible results, then suddenly found themselves destroying 4 out of 5 targets, knew something fundamental had changed. They might not have understood the physics of radio proximity detonation, but they understood effectiveness. Londoners, who'd endured weeks of V-1 bombardment, noticed when the flying bombs stopped reaching the city in significant numbers. The psychological relief was palpable. The terror that had gripped London through late June and July lifted in August, not because the Germans stopped launching V-2, but because British defences, strengthened by American technology, finally proved capable of stopping them. The story of August 28th. 1944, the day British guns destroyed 82% of incoming V-1 flying bombs, encapsulates several themes that defined the Second World War's technological dimension. It demonstrates the importance of fundamental research conducted before the specific threat emerged. The V-2 fuse program began in 1940, 4 years before the V-1 appeared, yet the technology proved perfectly suited to countering the threat. It illustrates the value of Allied cooperation, British recognition of the V-1 problem, American willingness to deploy classified technology despite security risks, combined industrial capacity to produce millions of fuses, and it shows how warfare increasingly depended not just on courage and tactics, but on the ability to innovate, to solve unprecedented technical problems, and to manufacture solutions at industrial scale. The German V-1 was a sophisticated weapon, the product of talented engineers working within the constraints of a war economy. It represented genuine innovation, the world's first operational cruise missile, decades ahead of its time in concept if not in execution. But it was defeated by a more sophisticated counter-weapon, developed by scientists working with greater resources, better cooperation between military and civilian researchers, and crucially, without the time pressure of imminent defeat. The V-2 fuse worked because American industry could afford to produce millions of them, because American scientists had the luxury of years of development time, and because American military planners were willing to deploy the technology when the strategic situation demanded it. For the individual British gunner on August 28th, tracking his 5th V-1 of the morning through his predictor sight, watching it disintegrate without understanding exactly why, the technical details were irrelevant. What mattered was that his shells, which had been missing targets for weeks, were suddenly, reliably, devastatingly effective. What mattered was that the terror weapon that had traumatized his city was falling from the sky in flames, mile after mile along the coast, a testimony to the fact that even Germany's most advanced weapons could be countered by Allied ingenuity. The morning of August 28th began with fear, another day of V-1 attacks, another day of civilian casualties, another day of inadequate defenses. It ended with confidence. The vengeance weapon, which had seemed unstoppable just weeks before, was revealed to be vulnerable after all. The technology that made this possible, radio waves and vacuum tubes, physics and engineering, American innovation applied to a British problem remained classified, but its effects were visible to anyone watching the skies over Dover that summer morning. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.